Hi everyone, my name is Jeremy and I will be presenting the paper Enhanced Video Game Live Streaming by Reconstructing an Interactive 3D Game View for Spectators. This was in collaboration with Daniel Vogel from the University of Waterloo. For the most part, the basic structure of streaming video games hasn't changed much over the past decade. When spectating on a 2D screen, this consists of picture-in-picture view of the streamer, composited with the main video game frame. In VR, this format largely remains the same, except that the 2D screen can now be viewed inside of a virtual environment where everything is encapsulated inside of a virtual cinema-like room. Though this approach has some utility, our intent is to expand on these basic formats to enhance the spectating experience for both desktop viewing and in VR by reconstructing aspects of the game for the viewer in real time. Specifically, we are interested in 1. How differing representations of the video game's virtual environment affect the spectating experience of the viewer. And 2. How can we reliably recreate these experiences in a generalizable and scalable way? We'll first talk about what the viewer experience is, and then we'll go into the system and infrastructure to make that possible. If we were to imagine video game spectatorship on a continuum, the ultimate form would be to have the viewer side by side with the player and given full agency over how they experience the stream, essentially giving the spectator access to the game directly. This, however, has issues around scalability, asset ownership, and developer effort to enable such spectatorship features. On the other end of the continuum is spectating a 2D rendering of the video game in screen space, which is scalable, generalizable, and is the most prominent mode of spectatorship today, as we just saw at the beginning of this presentation. In between these two extremes are intermediary states of spectatorship that utilize more data from the video game in different ways. This includes volumetric space that utilize 2D and depth data from the game, and world space that utilize the depth, matrix, and geometry data extracted from the game. These are the ones that we are interested in evaluating against the baseline screen space representation. Both of these are intended to be more immersively engaging than screen space, but with its generalizability and scalability intact. Looking from the user's point of view in VR, experiencing each of these levels, in screen space, the user is watching the video game stream in a theater-like space on a 2D screen, which is similar to consumer products like big screen VR. For volumetric space, the 2D view is now projected out into the environment. This creates a 3D effect, giving the spectator a new sense of immersion that the 2D plane in screen space cannot communicate, essentially rendering similar to a 3D movie experience. For the world space representation, the volumetric depth data is combined with positional, rotational, and world data to add context to where the stream is coming from. This allows the spectator to peer into the video game space and see where the streamer is watching events unfold from either a bird's eye perspective or dive directly into the action and watch as the streamer moves around the video game environment directly. These kinds of experiences are made possible through our enhanced video game live streaming system that handles 3 critical aspects: the game extraction process, the streaming process, and the viewer process. For the game extraction process, this handles extracting all the data from the game itself. We do this by intercepting calls to the GPU that pass through the DirectX graphics infrastructure interface. This provides us with the ability to then intercept the RGB, depth, view, and projection matrix data we need to recreate the experiences across our design space. For the streaming process, this runs outside the game and is piped data extracted from the previous plugin overlay. Here, the depth data is converted to a color space suitable for transport through standard MP4 compatible codecs like H.264. Here, all the data types, including the RGB depth, view, and projection matrix data, are encoded as separate channels into the MP4 stream. For example, in the video, you see the RGB and depth encoding running from the same MP4 file. Finally, the viewer process runs only on the spectator's computer. Here you see a Unity application ingesting the MP4 packets and then rendering the environment for the spectator by projecting out the geometry. Altogether, by using the data contained in the MP4 file, we can create the different levels in the design space we want to evaluate. And to evaluate this, we conducted a study with 18 remote users across North America and Europe. Each participant evaluated the three levels of our design space, which is screen, volumetric, and world, across 3 game types. Homeworld, Deserts Are Cracked, which is a real-time strategy game in a top-down bird's-eye view of the scene. There's Titanfall 2, which is a first-person shooter game with mechs. And Nier Automata, which is a third-person action role-playing game. These are then contrasted between both the desktop and VR versions of Spectatorship. The results of our study show that overall, using our enhanced video game live streaming techniques helped increase the spectator's perceived enjoyment when watching video game streams. And when they were in VR, the effect is even more pronounced, showing that the viewing these kinds of experiences inside of a virtual reality has a more profound effect overall. In summary, our high-level takeaways are: 1, spectating enhanced streams are overall more enjoyable than regular 2D streams. 2, spectating enhanced streams is generally perceived better in VR than desktop. And 3, in general, there are no notable differences between spectating the volumetric and world space reconstructions. That is the end of the presentation. Thank you for listening, and please see the paper for more details.